Good morning. Here we are once again. It's the physics video lecture, Physics 2A, video lecture 12. And I'm going to start with a couple of questions that were asked in the email for a couple of homework problems that we had. So let's go straight to homework problem chapter 3, number 44. So homework problem chapter 3, number 44, and that was a basketball player. So this is going to be a projectile motion problem. Now, I'll simplify right away. The basketball player is 2 meters tall and the hoop is 3.05 meters. So that's a 1.05 meter difference. So we're going to take the release of the ball here, and it's going to come in at some height h. We'll go ahead and call that height h here. It's going to be out at a distance d, and this is where the hoop is. That's going to be at a height h. Be at a height h above the ground, which is 1.05 meters. I won't be plugging any numbers in. We have initial launch angle. We have a V0, and the theta they're giving us is 40 degrees. The h here is 1.05 meters. And we have the d as well. The distance is 10 meters. So we're supposed to find this initial speed. Yes, we're supposed to find the initial speed. I'm just going to write down the formula that I had derived a couple of times. So y of x is equal to tangent of theta times x minus gx squared over 2 b naught squared cosine squared theta. Okay, now we don't usually want to just write down a formula. So where does this formula come from? It came from the x and y components with respect to time, basically from your free fall expressions, and then I plugged the, I solved for t and plugged in, and then I eliminated t, and now I have y of x. So that's actually the shape of this trajectory here. So what do we have here? This quantity goes in here, and x is going to be our d equals 10 meters. Here as well, g theta is 40 degrees. We have a cosine squared. So the point is, it's not a beautiful problem, but there is only one unknown here. Okay. So if you put in what I'm calling h here, that's the height at which it goes through the basket. Put in your 40 degrees. And by the way, don't plug them in yet. Just imagine that that's what goes there, there. There are no unknowns except for this V0 squared. So solve for V0. And it's not that difficult, but you do not want to plug any numbers in until you've done the required algebra to isolate V0, or V0 squared is good enough. Then you can plug in your various values. You'll have some complicated formula, just rearrangement of this formula, and then you'll get your answer. So this is to illustrate how important a labeled sketch is, and understanding where you're going before you start plugging numbers in. I know from experience, this is a beginner thing. You want to plug those numbers in as soon as you know what they are. But you don't do that. Just label, you know everything, it's all in front of you, and you're confident now. You just have to do some algebra, take off the V0, then plug in. So I'll even put this here for the record, solve for V0, then plug in y equals h, which I have right here, theta equals 40 degrees, x equals d equals 10 meters. Good, so there's that problem. And the other question was from chapter 4, problem 39. And I'm glad that was asked because it's a good, so chapter 4, problem 39. This is the bird feeder, and it's the perfect statics problem before we move on into dynamics today. So what we have is a mass, it's the bird feeder, and it's suspended by 2 strings. We have to make this artistic. Good luck on that. So it's suspended non-symmetrically. And what we're going to see, I'm going to label this theta 1 and this angle theta 2. And what I have here is m times g, right? The weight we've learned is the mass times the acceleration due to gravity. So we'll always do that now. We'll just, even if they called it F, or it doesn't matter, we'll mg. And what we have is tensions. So there's my T1, and here's my T2. Now what we have is that the net force equals 0. Here's my eraser. Okay, so the net force in this case equals 0. That would be the vector sum of those 3 arrows equals 0. What we do though is we break it down into the x and the y directions. So we say the sum of fx equals 0 and the sum of the y components equals 0. Because that's the nature of vectors, which is to say the nature of arrows. You can just add them up component-wise. Okay, so let's go ahead and do the forces in x direction. In x direction, what you'll notice is the angles as labeled there can also be seen in this way here. Okay. T1, T2. Be that as it may, we have to the left a component minus T2 cosine of theta 2. And to the right, you can see T1 is the hypotenuse, so we have T1 times the cosine of theta 1. Okay, so plus T1 cosine of theta 1 equals 0. What about in the y direction? In the y direction, we have mg pointing down, so we say that we have minus mg. And then pointing up, we have 2 components. We have T2 sine theta 2, T2 times the sine of theta 2, and T1 times the sine of theta 1 equals 0. Now, it takes a bit of practice to do this, so just because I did it and you copied this down doesn't mean you understand it. You really have to go over to these triangles and write them down and make sure you see exactly what I did here. Okay? So, draw this large and ponder it. T2 is the hypotenuse, cosine of theta is the projection in the x direction. The minus sign I put in by hand because it's pointing to the left. So once you do that for all of the expressions, I'm just going to put boxes around these. I like to do that sometimes just to focus our attention on what it is I'm talking about here. Okay, so we have 2 equations in 2 unknowns. Now I go back to the book. Yep, they wanted to know the tensions in each cable. So we have two equations in two unknowns. Let's write that down. Two equations for two unknowns. That means we have a chance of solving it. Okay? So T1 and T2 appear in both equations, and this one becomes algebraically a little bit involved. You have to solve for one of these, say for T sub 1, in this first equation and plug it in down here. Then you'll have a complicated expression in which the only unknown is T sub 2, and then you can solve for that. So with few exceptions, you always want to do the algebra first. At this stage of the problem, we're doing physics, right? We're applying our understanding of Newton's law, vectors, geometry. As soon as you plug numbers in, the physics is over and the mistakes begin. So you want to be able to set up the equations, understand what you're doing. So two equations, two unknowns, solve for one of them, for example, T1. I'll just continue with this example. So from the first equation, so let's label these 1 and 2. So from the first equation, what do I have for T1? T1 is equal to T2 cosine theta 2 divided by cosine of theta 1. As soon as you plug numbers in, forget it. You have that. Now you plug this expression into here. Now all that remains in here is a T2, and this T2 will be up there. It will be kind of complicated, but that's how to solve it. And another step of algebra will then take you to isolating T2, and then in terms of all these other things, then you can solve for it. We won't be doing anything that's more complicated than this. Okay, so go ahead and get your practice. But to realize that what I just showed you, that is the actual physics. And at some point, if you look at this form of it, you'll say, okay, that's the solution. Okay. The rest is just some arithmetic work to get you to the final number. Okay, so those are two good homework problems. We're on the subject of Newton's laws of motion, and I'm going to carry on. Quite a bit left to do in this chapter. Interesting stuff. All right. So I'll briefly review the three laws, Newton's laws of motion, and then we'll start systematically working our way through various examples. So, Newton's laws of motion once again. So there are three, and if we just want to write them down in shorthand, the first law, I'm just going to state inertia, and then we have mass, m, the unit of mass is the kilogram. We've got mass, m for mass in meters, just don't get confused, okay? Unit of mass is the kilogram. We can use an uppercase m too. Now the second law, the one we're going to work with quite a bit today, is that the net force on an object is equal to the mass times the acceleration. This is a very rich statement, okay, because it involves a lot. First of all, it's a statement about vectors. Okay, forces add like vectors. We're saying the acceleration is in the direction of the force, so we've got vectors here. When we say the net force, I won't always write that explicitly, but it's important. When we say the net force, that's the vector sum of the forces. So we're talking about vectors and their addition properties. Okay. Acceleration, of course, a very complicated problem here of motion. Okay, we've studied motion in a number of cases, and so this is the relation between forces and motion. And the mass comes into play here for the first time. And before that, we didn't know what mass is, and now we see it's a proportionality constant. It, has that property of inertia. If we just solve for the acceleration, net force divided by mass. Before that, we just had weight. We had force, we had weight, but we didn't actually have the property mass, okay, the mass property of things. Good. So that's the second law, and the third law is the law of interaction. And there's a good shorthand for that. Force that one object exerts on a second is equal and opposite to the force the second object exerts on the first. Vector equation, direction is the same with a minus sign in front of it. Equal sign means the magnitude is the same. Okay, so now let's start with the examples. I want to talk about the different types of forces briefly. We break them down into two principal types. One is the contact force. And this is what we were thinking of when we said a push or a pull. I pull on a string, I push on the wall, push on something, push on an object, and I feel the contact. Even the book, the book on the table here, right? That's a contact force between the book and the table. So we have contact force, push, pull, etc. And in particular, we often talk about what's called a normal force. So we're going to hear this word pretty often, normal force, and the term normal refers to geometry here. It means a perpendicular force, a perpendicular contact force. Okay, so let's just write perpendicular contact force. And the example, since I just had the book on the table, here's a table, here's a physics book. What are the forces acting on this? Well, we've now learned that the physics book has weight, and we'll just write mg there, but the table is also exerting a force on the book. Okay. This is the actual contact force. I'm just going to write n there for the contact, for the normal force, perpendicular to the table. So that plays a role, because another example would be a hill. Okay. Say somebody's on a hill. Dare I draw a skier on a hill? I'll regret this. Okay. There's a skier on a hill. So what's the force on the skier? We're going to say, okay, the skier has mass, but the hill exerts a force, the snow, on the skis, and you'll notice it's perpendicular. So over here, we would have a normal force pointing in that direction. Okay. So those are your contact forces. Perpendicular contact force we call a normal force, give it the letter N. You'll notice I've drawn the weight in twice already, and the weight is not a contact force. The weight is a field force. So under this heading types of forces, we'll put number 2, a field force. Sometimes we talk about a gravitational field. Okay, so under here, 2, field force. And an example would be gravity since weight is due to force of gravity, we have weight. There's also electromagnetic forces that you're going to study next semester. So I'm just going to write electromagnetic forces. You know, if you've held a couple of magnets close to each other, you feel that force and they're not in direct contact. That's called the magnetic force, the magnetic field force. Same thing works with electric charges. So I'm just going to write electromagnetic, and I'll put here physics 2B. Right? You can't wait to get there, but first you have to go through physics 2A. So electromagnetic forces, gravitational forces, those are field forces. They're exerted over a distance. When you're in free fall, then the force acting on you is the force of gravity due to the earth, and you're not in contact with anything. Nonetheless, you're subject to the gravitational force. Good, so we have those two types of forces. And now we'll do a couple of examples with them. A number of examples. So we're doing Newton's law. And there's an aspect of what we're doing now that is pure review, because the forces were there the whole time we were talking about free fall, when we were talking about projectile motion. So let's go ahead and when we were talking about statics and weight. So briefly, statics, which we have already done, statics refers to the net force equals 0 and the velocity equals 0. So things are at rest, the net force is equal to 0. That bird feeder example that we just did, a perfect statics example. Okay. Then when you have dynamics, that's when net force equals mass times acceleration, and you're actually talking about motion and how these things are connected. So these are the few examples I want to do next, some dynamics examples. Okay, I think we had already done the bucket. So the next one I want to do is the inclined plane. This one is really important. I was talking about how Galileo rolled things down the inclined plane in order to slow the action down and even figure out how acceleration is. So we're going to come back to the inclined plane, and I'll draw a nice sized wedge. So when you do a geometrical construction, go ahead and draw a big picture. And let's go ahead and call this opening angle alpha here. And we can imagine this wedge is on level ground. So gravity is pointing straight down. Okay, that's just an indication. Now, we're going to slide a weight down the inclined plane and just analyze this using Newton's law. So this is our mass M. Okay. Inclined plane, let's say no friction. Friction comes later. Right now it's going to slide with absolute smoothness. So the question is, what are the forces acting on this? Since I've got some different colors here, let's do our forces in blue. So we have mg, that's the weight, and as I showed before, we have that normal force, perpendicular, so that's n. right there. Any other forces acting on it? No, just those two. So this is called our free body diagram. We've attached these force vectors to our object here, and we know it's going to slide down. If we let go of it, it'll slide down the incline. So the next thing we're going to do is write down Newton's law. Again, it just doesn't hurt. It's a true statement. Okay. But what we see is we have to break it down into x and y coordinates. So I'm just going to say x here and y. That's what we're about to do next. But here's something that comes up. So things are mixed up here. What we can do is put our x coordinate parallel and our y coordinate perpendicular to the incline. This is just a convenient choice right now. It's up to you how you want to do it. Okay. So notice I've chosen the coordinate system. So we had a free body diagram. Should I make a list here? Free body diagram. And then the second thing, I chose my coordinate system. And now we're going to look at x and y. This takes a little analysis. So, but we know that vectors add like arrows, so we're going to take a perpendicular and a parallel component. Components perpendicular and parallel to the incline. So the question is, what is the angle right in here? Okay. And if you do a little bit of geometry and you name this, and you know that this is 90 degrees, I could call this beta, and I could call this little sliver there alpha. So this construction, you guys are responsible for this as well, to discover that that angle I'm talking about there is alpha. And now I will have mg sine alpha and mg cos alpha. So after you write all this down, your task is to start out with a fresh piece of paper and reproduce all of this without looking, okay? Because of course, as I do the construction, it all appears on the board, okay? So now in the x direction, what you can see is we have this vector here. So this little section there, mg sine alpha. So we have, and it's pointing to the left, so we have minus mg sine alpha. That's the vector diagram, and on the right side we say m a sub x, the coordinate of the acceleration in x direction. Minus sign, yeah, it's going to the left. Now in y direction, we have a vector n pointing up, and we have pointing down this dotted m red one here, so minus mg cos alpha. And that equals m times a sub y. So I've just translated my diagram into Newton's law. And these are just the two components of this equation. So, you know, always write this one down. Just it sets the stage for what comes next. Okay, so that's what I did. Now, it turns out that there is zero acceleration in y direction, because remember, the y-axis is perpendicular to the slope there. So this is actually 0. And the second of these two equations, let's number them, 1 and 2. The second of these two equations, from 2, we will say that m is equal to mg cosine of alpha. Important result. Okay. And from the first equation, we're just going to solve a sub x. Masses cancel. A sub x is equal to minus g sine alpha. So now we have the answer, the results, but we have to analyze it and see what it means. Okay. So I'm going to send this up and discuss what we've just figured out. Now, if this were a math class, then you'd just get these answers and put a box around and turn them in. But we haven't really, we've just begun because we have to understand what these expressions mean. So I'm going to check the clock. Good. So this is the analysis of the motion on the inclined plane. Good, I'll call this analysis. I'll just write analysis of the motion on the incline. We're going to start with this first equation, the normal force. I'm just going to rewrite it here and talk about the limiting cases, mg cos alpha. So limiting cases, that's worth putting down as terminology. Limiting cases. The first limiting case, suppose alpha is equal to 0. Alpha equals 0. What does that mean? That means I'm not on an actual incline, I'm just on a flat tabletop. If alpha equals 0, cosine of 0 equals 1, and the normal force is equal to the weight, it's just mg. Okay. So what you do is you think that through, and then you check it off. Okay. Normal force is just going to be mg. It's just like something like this book here resting on the table. Now, what about the limiting case alpha equals 90 degrees? Well, 90 degrees for an incline, so let my ruler be the incline here, okay? And that was the 0 degrees. Now I'm going to tilt it up to 90 degrees. And when it's 90 degrees, there's no sliding, there's just free falling. Okay. And if we look at the cosine of 90 degrees, that's 0. Then the normal force is equal to 0. So then n equals 0. Up here we had n is then equal to mg. And both of those make complete sense, so that's an important analysis. Next, we're going to do the analysis of a sub x. A sub x is minus g sine alpha. And we'll do the same two limiting cases. When alpha is equal to 0, the sine of 0 is 0. And the acceleration is 0. So if we have frictionless motion on a flat surface, it's just constant velocity. I showed it to you on the air track. I've shown it to you on the tabletop here with the other track. So there you have it. Alpha equals 0, then acceleration is equal to 0, and that means that v is constant. Okay. Very important result. On the other hand, if alpha is 90 degrees, yeah, then what? Alpha is 90 degrees. The sine of 90 degrees is 1. In that case, acceleration is just minus g, which means it's just free fall. It's free fall in the down direction. So that also, then a equals minus g equals free fall. Okay, so this is the difference between just getting an answer and understanding what the answer is. I want to point another thing out. If you plug numbers in here, you're not going to be able to do the analysis. Okay? You're not going to have the understanding. So the understanding is just as I've demonstrated to you. It's an understanding of the formulas and what they mean. Okay? It brings all of your geometrical knowledge into play, and the kinematics and dynamics that we've learned so far. Okay, so like I said, this is a really rich example. You think it's a humble example, but it has a whole lot going on in it. Good. And you know, if you could reproduce this discussion just from scratch, you would have learned a lot. Okay, let's see what's next on our agenda. We have many types of problems. That was a properly dynamic problem. Let's see how much time we have left. Now we'll do a little more. Frictional force or two-body problem. Let's do friction. Force due to friction. How do we build friction into this situation? You know, just pushing a book across a table takes some doing. There's quite a bit of friction here. It's not a frictionless tabletop at all. So there must be a force involved if I have to exert my muscles to continue pushing something. So force due to friction, I'm just going to define it for you. I have demonstrations for this as well with scales and what have you. We'll bring those in next time. Okay. Force due to friction, we'll start with a tabletop. And maybe I'll discuss what the demonstration looks like. You've got a tabletop and you've got a mass here. And say you want to pull, use different color. Say you want to pull to the right here. Say you've got tension. Okay. You want to pull it and it's not budging. Well, the only way that's possible is if there's some friction pulling in the other direction. So I will use the lowercase f for the friction force. So if I'm pulling and it's not budging, there's got to be a friction force pulling in the other direction. And what you find is if you plop a bunch of extra mass, a bunch of extra weight on top here, the friction is even more tenacious. If this were a sled, you know, and somebody jumps on it, it's going to become more difficult to pull as well. So let's look what we have here. We have the weight. We're trying to pull the thing, and we have this friction that increases as you put more weight on it. So what is discovered is that the friction is proportional to the normal force, and it's opposite the direction of motion, or of attempted motion. So friction, so the friction force F is equal to mu times N. So mu is a Greek letter, and it's used as the frictional coefficient, and N is the normal force. So we could put in words here, friction is proportional to the normal force. To the normal force. And then there's the actual expression. This is the Greek letter mu, and mu is the proportionality constant. And you'll notice forces, friction is a force, normal force is a force, so mu is dimensionless. Mu is a dimensionless number. And how to determine mu is actually pretty interesting. Of course, it's different for different substances. Some things are slippery, things are not slippery. And it's, in fact, it'll be the coefficient of friction for the combination of two substances that are in contact with each other. So yeah, mu is called the coefficient of friction. Coefficient of friction. So there'll be a chart in your book, I think, with some coefficients of friction. Typically less than 1, it all depends. I think I'm going to end this with one more sketch. Coefficient of friction. Yeah. In fact, I'm going to start a new picture here. But we'll title this Incline with Friction. Inclined plane with friction. And I'm just going to relabel. So it's the same scenario as before. Here's M. There's the incline alpha. G is free fall, right? Gravity. We're just going to include the friction here. So now if we have mg and n, we also have to include a frictional force, which will have opposing the direction of, say, this thing sliding down. And to tackle a problem like this, you would do what we had done here, but you would have to include this friction force. And you know its magnitude is mu times n, and we were able to solve for n, so it's the same problem we solved with an added force in it. So yeah, be careful, note the directions. This n is normal to this incline. This force is parallel to the incline, but its magnitude is proportional to the normal force. Good, I'm going to leave it at that and see if we can come up with homework for lecture number 12. This will be in chapter 4. Should be some good ones. Yeah, there is a section on connected objects. We're not doing those yet. So that puts us at a disadvantage. Okay. Let's do chapter 4, number 79. And this is a horizontal problem. And it involves friction. And 77. Those are pretty good. Good. We'll do these two. They involve friction. They involve inclines. They're actually pretty rich in content. And what we're going to do next time is systems of connected objects, and That's when we can really bring everything together. So these will be good. Okay, enjoy. See you next time.